by Major Dr. C.S. Sanghvi sir, and he will be dealing with the topic of experiments in earthquake engineering laboratory to demonstrate effects of seismic force resisting systems. Now, as I mentioned in the earlier days of this STTP as well, that we have a very fully furnished and a quite popular earthquake design laboratory in our college, and Dr. Sanghvi played one of the pivotal role in the establishment of that laboratory. The laboratory is one of its kind in the entire state, or I would say the nation, because it possesses numerous shake tables. And I would tell you that Sanghvi sir is constantly involved and indulged in the activities to bring some innovations and some modification in the shake table. Is also regularly working with students and collaborating with students and other institutions to bring innovations in shake tables and other devices. The the laboratory is also comprising of low and high frequency random motion shake tables. It also has sophisticated instruments such as spectral analysis surface wave system, portable universal data logger, vibration analyzer, uniaxial and triaxial sensors, and many more. So I would like to ask Sanghvi sir himself to continue with this session and tell everything in much detail. Over to you, sir.
Yeah.
Thank you.
Yeah. Thank you, Aditya. Okay. Very good afternoon. Again, this is a post-lunch session, and again, I'm always believing that post-lunch session is a little bit difficult for the participants, and particularly for the participant, right? But I will not going to bore you. Today we are talking about the some experimental investigations, or which is taken place at LD College of Engineering, and how can we move forward as far as testing is concerned, right? So right now I'm sharing my screen, and is it visible?
Yes, sir, absolutely.
Yeah. So under this particular program, design of confined machinery buildings for earthquake disaster risk mitigation in India, we talk about the machinery buildings all the time. Here we try to include all types of structures, and the topic is experiments in earthquake engineering laboratory to demonstrate effects of seismic force resisting systems. So we will talk about the different lateral load resisting systems, and how the different features of the our building or structure will affect the performance, that we'll discuss in this particular lecture. You see, we'll talk about the hazard vulnerability in India. If you look at the Indian subcontinent, then we have 54% of land which is vulnerable to earthquake, 8% of land vulnerable to cyclone, 5% land vulnerable to floods, right? So this 54% land, I'm talking about zone 3, 4, and 5, right? So more than 50% land is vulnerable, right? So which is alarming, and I think we have to seriously think about our earthquake preparedness, and we have to work for earthquake safety in the country. If I'm talking about the earthquakes, then the 12% land is liable to severe earthquakes. Severe earthquakes means they are in zone 5. These zones are susceptible to intensity 9 and above, right? These are the expected intensity in these zones. So 12% land which is in zone 5, which is quite high. 18% land is liable to MSK 8 intensity, means they are in zone 4, and 27% land is liable to intensity 7, means we are talking about the zone 3. For example, Ahmedabad, Baroda, Surat, they are in zone 3 as far as Gujarat is concerned, right? So like if you talk about Jabalpur is also in zone 3. If I talk about Latur or Uttarkashi, they are in zone 4, And when we're talking about the north, some part of the north, like Srinagar, some part of northeast region, Meghalaya, Manipur, Sikkim, and all that, even Kutch, it comes under zone 5, right? So this is the hazard vulnerability of India. And in the last lecture, we said that the loss of life and economic loss is associated, and maximum loss is during the earthquake. Right? This is a philosophy where damage is allowed, but collapse is not allowed. So we always believe that our structure will enter into inelastic zone when it is subjected to earthquake, right? In case of a major earthquake, right? So as a philosophy is concerned, the philosophy is very simple. It is a three-step philosophy that under minor but the frequent shaking. Generally, we talk about a non-structural damage and damage, structural damage part, right? So when minor shaking uh, uh, taken place, which is quite frequent, right? So during the minor shaking, energy released during the earthquake is less, and our structure is able to absorb that energy, and therefore we are not expecting any structural damage. Non-structural damage may be there, which may be repairable. Under moderate shaking, but which is occasional in nature, then we are expecting a heavy damage in non-structural member, but repairable damage in structural members. And under the strong shaking, but which is generally this strong shaking is rare. Strong shaking means I'm talking about earthquake like Bhuj. So in case of earthquake like Bhuj, we are expecting a very heavy damage which may not be repairable as far as non-structural part is concerned. And in the structural part or structural members, we expect heavy damage, right? Heavy damage, which may not be repairable even, right? It is possible that after earthquake you have to demolish that particular building, but you you should not observe any collapse during earthquake, right? So damage is expected. The damage, the amount of damage which a structure experience, it may be in the range of low to high, but your structure should not collapse during earthquake. That is the bottom line, right? That part you have to understand. Collapse is not allowed at all. So we in the last lecture we said that earthquake do not kill, but unsafe buildings too. So it's a man-made disaster, and we have to focus on buildings. We have seen this slide, and we say that under the previous earthquakes, we have seen tremendous failures, right? Whether it's America or Japan or Turkey or India. So during these earthquakes, uh, we have seen the failures of the structures like bridges, buildings, and many others. This 95 Kobe earthquake is known for the bridge failure. Right? In the last lecture, I told you that Japan is considered to be the best as far as earthquake preparedness is concerned. And even though Japan has observed such kind of devastation in 1995 Kobe earthquake, even we have seen the devastation in 2011 earthquake. Right? We'll discuss that later on. But right now, we want to say that during the earthquake, we have seen collapse of the buildings. Maybe in the developed country, the number of building collapse are less, and a developing country like India, um, we have more casualties or more collapses. Right now, we come to the our main topic. That is, we talk about the various uh, conventional lateral load resisting systems. Right, we are knowing that there are two types of forces, gravity loads and the lateral loads. When we are talking about the gravity loads, then it is acting in the direction of the gravity, right? And um, the load will be transferred from slab to beam to column and foundation, right? And when we are talking about the columns will carry axial force in case of gravity loads. Most of the time moments will be there, that is the additional part, but the primary action is axial compression. But in case of a lateral load, the action on columns, shear walls, or the vertical elements is changed. Because of the lateral load, the shear and a moment is going to come on uh, your vertical elements, right? Now these vertical elements are responsible to transfer the lateral load. Right. So it is very important for us that we have to design this vertical elements in such a way that it will able to transfer the earthquake force which are generated during the earthquake. Right. Uh, Now, you see why uh, uh, the columns are critical in this case, because the column is vertical and the load acting on it is in horizontal direction. So uh, the load is not acting along its longitudinal direction. Right? That is the main problem. And so when the load is acting in the lateral direction, so shear and moments that will come in picture instead of the actual force, right? So we have to design this element in such a way that they should take moments and shear. So we talk about the various conventional lateral load resisting system. They are columns, shear wall, bracing system, it may moment MR frames, which is a combination of beams and columns, tubes. Right? So these are the systems generally we are placing in the uh, our structure to resist gravity loads as well as lateral loads. Right. So here the three main structural systems we are putting here. This is a moment resisting frame, which is made up of beams and columns. Right. We have a braced frame. Now bracing, generally this bracing will observe during in a steel structure, and this is a structural wall or shear walls, right? So you can see this picture. This is a simple MR frame, is combination of beam and column. You can see in a close view. When we are talking about the braced frames, the different types of bracings available: X brace, chevron brace, eccentrically braced frames, right? And you can see the this application in the real structure. The bracings are provided, right? Now the work of the bracing and the work of the shear wall is almost same. These bracings are provided in most of the time in the steel structures. The purpose of providing the bracing is to increase the stiffness, right? You can see the closure view of this bracing system. We have a structural wall. Structural wall, it may be a shear wall, it may be a flexural wall. Yeah, walls are classified on the basis of aspect ratio, or it is also classified on the basis of the behavior, whether it carries a large shear, it is a shear wall. When the flexural deformation governs, it's a flexural wall. You can see the construction of a shear wall. Before 2001, people are assuming that the construction of shear wall is difficult, but it is observed that the construction of shear wall is very easy, right? And nowadays, most of the structural engineers are preferring shear walls, and I think they are nicely executed even. Right? So you can see it may be a single layer reinforcement, double layer reinforcement. It depends on the thickness of the shear wall. Uh, so you can see this. Right? These are the, and we may have a dual system. We have a moment resisting frame, and you can add a shear wall in it to increase the stiffness, to increase the lateral load capacity. It depends, right? So it's known as a dual system, and these are some cases of dual system, right? We have some special structural system also: tubular systems, frame tubes, truss tubes, bundle tubes, shear wall with outrigger. So these type of systems are also we have observed in the case of a tall structures, right? So we are not going to discuss that part. We directly go to the main part. That is the why the earthquake lab is needed, right? So the first point we'll want to discuss is earthquake is a random strong ground motion, right? Now, uh, if you have observed the time history of earthquake, you find that uh, time history means I'm talking about the acceleration versus time curve, right? So if you talk about the earthquake time history, then you find that the earthquake carries various frequencies, right? And it is randomly changing. These two things are there, and at the same time, we have to understand that what is the peak acceleration observed during the earthquake. What is the peak ground acceleration? Right. So this earthquake motion is very random in nature, and uh, uh, we have to understand the earthquake ground motion. Once if we understand earthquake ground motion, then we are able to uh, understand the effect of this earthquake on our structures, because we know our structures. If we know earthquake, then we can predict that what is going to happen to particular structure, right? So that is to be needed. And therefore I'm always saying that response of structure to this random ground motion is very complex, right? If I'm talking about the structures, if structure is symmetrical, definitely it performs well. If it is unsymmetrical, then torsion is going to introduce in the system. Then it will become very difficult for us, right? And therefore, we have to be very careful. So, uh, uh, you see, to understand the behavior of structure under the gravity loads are very easy, right? But to understand the behavior of structure under dynamic load is a bit difficult, right? So again, I'm telling you, you must know the structural parameters of your building, right? And if you know the earthquake properly, then you are able to understand what are the effects going to cause on your structure, right? So that we can predict. Earthquake analysis we discussed in last lecture, that we are performing either static or dynamic analysis. We assume that earthquake load, we assume is a static load, and then we perform a static coefficient method. We have performed the analysis through static coefficient method, right? But this static coefficient method is more conservative. It will give you a higher value. So it is not a cost-effective solution on the other side, we can say. So if we perform the analysis through static coefficient method, generally it gives the higher value. And when we design for that, our structure elements basically designed for the higher forces. So most of the time we say that dynamic analysis should be performed. So you can make your structure economical, because you have actual forces which are actually acting on your structure, and for that you are designing your structure, right? The code provision IS 1893/2016, it is there. We have to understand that properly. We have to understand that earthquake forces are much bigger than the design forces, right? This is what we understood, because we allow the damage in our structure. When we allow the damage in the structure, it means the earthquake forces are much larger, and we heavily rely on the ductility, right? Basically we try to absorb the earthquake energy, right? We try to absorb earthquake energy. So the whole earthquake engineering design philosophy based on absorption of the energy, that's all, rather than designing for the maximum force. No, we are not designing for the maximum force. We design for the certain level of the force. Right. So design philosophy is saying that collapse is not allowed. Right. When one earthquake comes in a region, then at that moment we see the disaster, and after that we try to refine our codal provisions. Right. This is happening, and this is what happened in 2001 also. And after 2001, uh, um, our codes were revised. You see, our earlier code was of 1984, right? And the next revision was 2002. So it requires almost 18 years to revise that code. And you'll be surprised that the revision of IS 1893 was started in 1993 after the Latur earthquake, and in 2002 it came. So it came after a Bhuj earthquake. So we can say uh, the one earthquake started the revision, and another, and it was completed after the another earthquake, right? So we have to be a little bit serious. We have to contribute as far as the uh, code development is concerned, and we have to contribute in a way that the work we are carrying out at our institute level, that should be documented properly. And uh, we have to give our inputs when the code is coming out, when code is, you see code is asking your suggestions, and they try to include your suggestions. If your research is perfectly okay, then definitely the code is going to take your research work in the code even, right? So we have to contribute. Now uh, uh, you see, why earthquake lab is needed? Because laboratory testing of a physical model to earthquake simulation provides a practical aspect of complex behavior of the structure. So when I'm performing any test on a model, right, then I can see the behavior, and I am always believing that seeing is believing. If you see the behavior, definitely you don't have any other option to reject it, right? So if you see any behavior, then you will remember it for a longer time. Actually, what happens when I was studying, we don't have the earthquake lab, and we have many questions, and when we are asking the questions and professors are answering, and we believe that okay, this is correct. But if I'll see the same thing in the laboratory, then I will believe those theoretical concepts, right? So shake table is one of the main main equipment of the laboratory testing, and the models are tested, right? So the which type of laboratory testing generally perform, right? So when we perform a test on a model, we go for the free vibration test. The free vibration test means what? The free vibration test means if you have any system, you disturb it initially. You just give certain displacement and then allow it to vibrate. Right? So we are going for only initial disturbance, and the system will vibrate on its own elastic property. It is known as a free vibration. Right? So we are just disturbing the system. We apply certain displacements and then release it, and the system will vibrate on its own elastic property. That is initial displacement test. Same way, under free vibration, we are applying the initial impact. Right? We apply the impact. So then your system will vibrate on its own elastic property. That is the free vibration test, but having the initial velocity. Right? So either free vibration test can be performed through initial displacement or initial velocity. Then we go for the forced vibration test. These forced vibration tests are the resonance test. Resonance test means we are knowing what is the frequency of a building, and then we apply those frequencies, right? So during the that your structural system will give the maximum response, right? Maximum response. That is the resonance test. So resonance means it is a phenomena where frequency of external excitation force matches with the frequency of the structure. Then your structure is going to exhibit a large response, right? So that is on the resonance. So we perform resonance test. Variable frequency sinusoidal excitation. So basically we are applying a sine, uh, uh, the external excitation force in form of a sine curve, right? So we are applying, it will increase in one, means we apply in one direction and then it also apply in the other direction, right? Then transient excitation, vibration table test, quasi-static load test, pseudodynamic test, real-time dynamic hybrid test, ambient vibration test. So these are the various tests we are performing. I'm not going to discuss all this, but what we have performed in our laboratory, we'll discuss those. Right? You perform the free vibration test. They are initial displacement type and initial velocity type. And in force vibration test, we perform resonance test. We perform a variable frequency test and the shake table test. Right? So we'll see this thing. Right? Now, if we want to develop earthquake lab, then what we need actually. So to perform a dynamic test, we require three major things. The first is the equipment to provide the dynamic force, because if we say if we want to study the behavior of our structure under earthquake force, then earthquake is needed. So we need an earthquake simulator in the lab, and it is known as a shake table. It is shake table. Second, you want a prototype, scale, or experimental model. So we want to perform test on structure. So either a full scale model, so you need a hi-fi facility. If you have a small scale shake table, then you also scale down the structures, right? So you can have a different types of model. It is a scale model, or it may be a half scale model, it may be a full scale model, it depends. And we require instrumentation setup. Basically we perform the test, but we have to measure the response of the system, right? And therefore we need a instrumentation setup. Now this instrumentation setup is having a data acquisition system, and this data acquisition system is uh, is complemented with the sensors. So sensing units also we need. So the combination of sensing unit and data acquisition system, it will capture the response of the model, right? This is the most required, right? And if we have a good data, then we can analyze it, that what are the effects of earthquake on a real structure, right, or on a model. Now what is shake table? We'll start. So again, I'm saying we have three components: shake table, model, and instrumentation set. These three things are required. So we go one by one, and we'll take up this. The shake table. What is shake table? There is a laboratory equipment which is capable of reproducing the motion of ground, right? So you see, it depends which type of laboratory facility you have. For example, if you look at the Japan is having a wonderful facilities. So they can input the real earthquake ground motion, right? Many IITs is having such facilities, right? So uh, they can reproduce the earthquake ground motion. But if I'm talking about the lab we have at LD College, uh, we are not saying that we are exactly applying the ground motion, but we are applying the sinusoidal excitation, right? So it is a harmonic excitation. Uh, that depends on the type of facility you have, right? So it allowing for the control testing of structures subjected to earthquake. So that is needed. Now, this shake table is having 6 degrees of freedom, right? This is the best one we have. So 6 degrees of freedom, it means it is having a transition in X direction, Y direction, and Z direction. At the same time, a rotation about all the three axes. So the 6 degree of freedom system, that is the best shake table. But as far as the LD key is concerned, we have a uniaxial shake table, right? So this 6 degree of freedom shake table is capable of producing the actual earthquake, right? And basically, if you have a good system in form of a servo hydraulic system, then a complex earthquake ground motion can be given as an input to the structure. Right? Prototype and scale models are tested in the laboratory. Right. Shaking table helps in investigating both linear and non-linear structural behavior. So there are two things. If you perform the test, you can see the behavior, and you are testing in such a way that your model is entering into the inelastic region, right? It means non-linear response, right? Then your structure will get damaged, and you can understand what is the capacity of the model or the structure. The shake table test deals with the nonlinear studies also, right? So here the certain facilities I am showing you. This is an earthquake simulator in University of California, Berkeley. Right. So this is if you look at this, then the specification is it's a 20 feet by 20 feet size, and payload capacity is very high. Servo hydraulic actuator controller. Right. So Basically, it is servo hydraulic. So you can input the real earthquake time history, and you can test the model under the time history. It is horizontally driven by the 8 actuators and vertically by the 4 actuators. So we have 4 actuators in X direction, 4 actuators in Z direction, and 4 actuators in Y vertical direction, right? And this is very important. The horizontal acceleration up to 1.5 G. Now this you have to understand. What do you mean by 1.5 G? This is very important for us. You see, when I'm talking, what is G? If I'm saying 1G, 1G means what? So in case of earthquake, generally we are normalizing weight with respect to gravitational acceleration, because we are knowing weight is mass into gravitational acceleration. Right? We are knowing that the W is equal to mg, right? W is equal to mg, and what we do, we are normalizing with respect to g. So we are dividing, sorry, we are dividing by the mass. So here mass is constant, so we are dividing by the mass. So what we are saying, that the weight is 1g, right? So when I'm saying the weight of the structure is 1g, it is 1g, right? Weight of the structure is 1g. 1g means it's the weight of the structure, mass into gravitational acceleration, total weight. Now this shake table is capable enough to give 1.5 G to the that type of load in horizontal direction, right? That acceleration it can generate, right? The 6 degrees of freedom, right? 2 transition, vertical, and 3 rotation. I told you that two translation means horizontal directions, 1 vertical, and 3 rotations, right? So this is one of the best facility available in the international universities. You can see this is the uh, uh, earthquake simulator at NID Japan, and this is considered to be the one of the best facility available internationally. And you just look at the size and everything. 1200 ton, that is the capacity, right? Payload capacity is 1200 ton. So you can test up to this. Like if I'm talking about the LD, we can test up to 1 ton. Now there are 12,000 ton, which is quite high. And you look at the size, 20 meter by 15 meter, right? 12 meter by 15 meter. This is one of the biggest shake table we have, right? And it is again the servo hydraulic, and these are the certain parameters, right? This the maximum acceleration, how much acceleration you can impart, or velocity. Displacement is 100 centimeter and 50 centimeter in the vertical direction, right? So you have a 100 centimeter displacement, plus and minus both way, right? So that is to be appreciated, right? This is the secure facility available at IIT Roorkee. Here you can see the view of 1/5 scale model of 7-story RC frame building at University of California, Berkeley, right? So this is a 1/5. Just look at the 1/5 scale model of 7-story RC frame, right? So we come to the another part, that is I told you that the shake table is having 6 degree of freedom, right? 6 degree of freedom. The 3 translations means X direction, Z direction, and Y direction. So 2 horizontal direction, 1 vertical direction, right? And 3 rotations. So generally, you see, the rotations are not important for a normal building. The rotations we have to consider in case when your structure is too long, right? Now if I'm talking about the wavelength of earthquake, then it is 2.5 to 3 kilometers, right? That is the wavelength. And now if I'm talking about the size of my building, the size of my building may be a 50 meters, right? 50 meter or 80 meter. right? Or 100 meter. Now, if I'm talking about large size, it's 100 meter. But wavelength of earthquake is 2.53 kilometers. It means the foundation, all foundations of this building will experience the same ground motion, right? But if you think about a pipeline, for example, the pipeline is 500-kilometer long. Now, when it is subjected to earthquake, what is going to happen? We are knowing the length of pipeline is 500 kilometers, and the wavelength of earthquake is 2.5 to 3. So you have a differential settlement or differential action on the pipe, right? So therefore, if you consider a rotation in case of long structures, it will be okay. Otherwise, you can consider only the translation, right? Only if you consider the 3 translation component, 2 horizontal and 1 vertical, then it will be fine, right? So out of 6 degree of freedom, we are not considering the rotational component right now. We are only considering 2 horizontal direction and 1 vertical direction. Now again, vertical direction. The vertical direction is generally not important for us. Why I am saying this statement? When I'm making this statement, I understand that my structure is away from the epicenter. My structure is away from the epicenter, right? I'm knowing that the earthquake is having horizontal acceleration and the vertical acceleration, right? But I'm knowing the vertical acceleration of earthquake is reducing very sharply with the distance. Very sharply with the distance. If you go 20 kilometers away from the epicenter, then vertical component of the earthquake is almost negligible, right? And therefore, we are saying that the most of the structures will not experience the vertical acceleration to that extent, and but the horizontal component of the earthquake will travel for a long distance, right? So the horizontal component is very important to study the behavior of the structure, right? So vertical component we are generally not counting. So this is not counted uh, uh, when we make the shake table. So 2 horizontal component we have considered, right? Now 2 horizontal component means either the shaking is taken place in the x direction or in the z direction, right? So the predominant direction is a horizontal. So we talk about the horizontal. We could talk about the uniaxial shake table, right? In horizontal shake table, moment is equivalent to the horizontal shaking of the ground, right? Now, question is arise that the uniaxial shake table is okay because the shaking is taken place in x and z direction. 2 directions the shaking is taken place, and we are talking about only 1 direction. The code is saying that you have to consider 1 direction at a time, right? So what we do here, we test our model in 1 direction, right? And then we change the orientation of the model at 90 degree. So with the use of the uniaxial shake table, we can test the same model in other direction, right? So therefore, if you have a uniaxial shake table, that is the primary requirement. I'm not saying that is the ultimate requirement. It's a primary requirement for the earthquake lab, and you can study the behavior of model, and you can study behavior of the structures through these models, right? So uniaxial shake table will work, right? Why I'm saying this? I'm saying this because if you want a 6 degree of freedom, then it is very costly, I tell you, right? When we are talking about the earthquake lab, generally the lab is costing more than 1 crore, 2 crores. It depends. If we have a laboratory like what Japan is having, it may cost maybe more than 100 crores, 200 crores. It depends, right? So generally, if it is costly, then the educational institute will not procure such facility. It should be central facility, right? If it is too costly, it should be central facility. If any institute has to develop this facility, then it should be a low cost of facility, right? Then the institute can procure. So the thing is, now we conclude that uniaxial shake table will serve the purpose, right? Uniaxial shake table will serve the purpose. Now, I'm showing you the pictures of earthquake engineering lab at LD. This is the shake table, which is size is 8 feet by 4 feet. 8 feet by 4 feet. And this is the first shake table we have developed at LD College. This shake table was developed from the waste available in the store. Right. This shake table was developed by the student with the help of fabricator. So this shake table was developed. Still, it is working. This shake table was developed in 2003, and after 20 years, still it is in a working condition, and we are testing uh, the models on it. But this shake table is a low frequency shake table. Payload capacity is also low. So here we are testing of flexible models. That is the first part. The second is, this is the shake table we have developed with the help of GSDMA, and this is a small shake table, right? Now you say this size of the first shake table is 8 feet by 4 feet. Then actually what happened in 2002, we have placed a request to Gujarat Council of Science and Technology that we need a grant to develop shake table, and we have sent a proposal to the Guj cost, and by the time we have not received any response in a year. By that time we have developed this particular shake table with the help of the available material with the department, right? And after development of this shake table, the Guj cost has also given us grant, and they have given us grant, and they said that you develop a shake table. At that moment, the question will arise that one shake table is already there, then are we need another shake table? So in that case, what we have done is that what are the limitations of this shake table, that we have to understand. This is a the first shake table was a low frequency shake table. So we need a high frequency shake table so we can have some more models. So we have developed a 2 feet by 2 feet shake table, and which is a high frequency shake table, right? But here we can only impart harmonic motion. Same way, in the first shake table, we are able to impart harmonic motion, right? So these two shake tables have been developed at LD College, and these are the uniaxial shake table. Then we have developed, we said that, okay, what are the limitations of these two shake tables? The limitation of these two shake tables are we can apply only harmonic motion, that's all, right? So we have sent a proposal to Gujarat State Disaster Management Authority, and we said that we want to develop earthquake engineering laboratory setup. And basically, when we are talking about the earthquake laboratory setup, then people will feel that it is too costly, so nobody is purchasing. And if you look at the condition in Gujarat, there was not a single earthquake lab in the state of Gujarat before 2001, right? So we sent a proposal to the GSTMA, and we said that we developed an earthquake lab in such a way that the cost will come down. And the cost of developing this shade table, it is only 5 lakh or 5.5 lakh. This is the grant we needed to develop the earthquake lab. Right now, the 5.5 lakh is very small amount, right? And when we asked this amount, it was sanctioned by the GSDMA, sorry, and we have developed this shake table. Now, while developing this shake table, we kept in mind that the earlier shake tables having certain limitations. These two shake tables can apply only harmonic motion. So therefore, in this shake table, we try that we can apply random motion, right? So we have developed this shake table with the help of Gujarat State Disaster Management Authority, and it was costing 4.5 lakh in 2007, right? Now it is costing only 6 lakh after almost 18 years, 16, 18 years, right? So our purpose is that we don't want to increase the price of this shake table. So we have developed a very low cost shake table. Now we can see this high frequency shake table. Here you can apply the frequency up to 15 hertz, and just for a moment, Okay, sorry. Can you see my presentation?
Yes, sir.
Yeah, okay. So this is the high frequency shake table with a servo motor, and each impart the random motion, right? The frequency range is 0 to not 25, it's 15 hertz. Payload capacity is 500 kg, but you see the payload capacity we designed for 500, but actual capacity we tested up to 1000 kg also, right? The stroke length, the displacement is 2 mm to 60 mm, and it is mounted on a pedestal, right? So this is about the shake table and on which we have performed the experiments. We need a instrumentation setup, right? I told you that we have to capture the response of the model, right? And we have a 16 channel vibration analyzer. This is 16 channel vibration analyzer, and we have the uniaxial sensors and the triaxial sensors, right? The sensors we have now, at a time we can capture 16 records, right? So this will help in that, because we have 3 triaxial means 9 plus 6. This means 6 uniaxial sensors we have. So 15 we can capture at a time, right? Now, when we're talking about the experimental setup, what we need actually, right, in experimental setup. So first thing is you have to determine the property of the model, right? Because you are performing test on a model, so you know everything about the model. That is to be required. For example, which material we are using. For example, we are using steel. Then what is the value of E? What is all other property, relevant properties, right? We have to determine the stiffness of the model, because we are knowing that earthquake loads are distributed as per the stiffness of the vertical element. So we have to determine the stiffness of this model, right? And we have an impact hammer. We have uh, uh, with us. So we have a shake table. So we perform this test. So we perform the impact hammer test. We perform the shake table test, free vibration test, right? So this is a very simple arrangement we made to measure the actual stiffness of the model, actual stiffness, right? How we measure that I will tell you. You see, if this is the model, this model is capped here, right? And we are restraining the movement of this slab one. It is a two-story model, right? So we are restricting the movement. We are holding it, and we only allow the top story or the top floor to move, right? It will be like this. Right? So it is a two-story model. Now here what we are doing, we are applying the load at the floor one, right? So we can measure what is the stiffness of the first story, and then we are holding means we are restraining the first story, and then we apply load to the top floor, right, in a horizontal direction. So we can measure the deformation. You can see here the dial gauges are there, right? Here you can see the dial gauges. So this dial gauge will measure the deformation. So the first, here the restrainer is provided, and here we measure the deformation. We get this second stiffness, the stiffness of the second story. So the second story stiffness we are getting, right? So you have to determine the stiffness of the model in a real sense, I tell you. Right? Theoretically, we can find out, but that may not be the exact one. So here you get the exact stiffness of your model, because in your model, it is very difficult to model the boundary condition, right, in the software. Suppose if I'm uh, analyzing my model in the software, then I have to give uh, the, uh, the boundary conditions. If I have to give the uh, suppose a beam column is there, then it's a rigid or not, and in real sense it performs in some different way. So the theoretical result and the practical result is having some different values, right? So uh, that is the how we measure the stiffness of the model, which is very important. And then we perform the free vibration test. Free vibration test means what? Again, I'm saying the model is there and you disturbed it initially. Once you disturbed it initially, and then it will vibrate on its own elastic property, right? That is free vibration test, right? And from this test we can measure the natural period of the building, and we can also determine the damping. Now when we disturb it, then what happens? The maximum deformation is at the starting, and then it will reduce with the time, right? So here you can see the curve. So here the maximum displacement, and then this displacement is keep on reducing in each and every cycle, right? So this is happening. So why it is reducing? It is reducing because the damping is present in the system. So by the free vibration test, we can measure the damping present in the system. That is one. The second is we can measure the natural period of the structure or model, right? These two things we can do here. So this is the equation by which you can determine the damping. This is the damping, right? And this is the equation which is given in the book of Chopra. You can determine this way, right? So it depends on the this measurement of the displacement of the cycles, right? It depends. So I'll show you how it is performed. So it is a video. I think you can appreciate that video to understand. This is a free vibration test. You can see this is the model we have, and what we are doing, we have to disturb the system, right? We have to disturb the system. So you can see these are the sensors. Yeah, these are the sensors placed. So this sensor will capture the acceleration of the model with the time. You see here only initial displacement is given, right? And he is relieving. Now the structure is vibrating, right? Structure is vibrating, and you can see the sensors are placed, and the sensors are recording the motion of this model. The sensor is recording motion of this model. Right now, you can see this is the data acquisition system we have, and here in the software you can have a record, right? You can see this record, right? So we have a record of the response of model, right? So this is how we perform the free vibration test, right? And through this free vibration test we'll get the natural frequency of this model, and at the same time what is the damping present in the system, right? Again, I'm running this video because you have to understand this part. This is very important for us to understand the first video, and after that the other small videos we have, so you can understand the other part also. So here the sensors are placed, and we want to perform free vibration test. So the student here is disturbing the model, right? Simply he is stretching the model and relieving it. So it is relieved, and you see this is having its own elastic property, right? And therefore it vibrates on its own elastic property, and The response of this model is captured through the data acquisition system, and this you can see here. This is the response we have, right? So here you can see it's a reducing response, displacement is reducing, that you are getting here, right? So this is known as a free vibration test. The another thing is the impact hammer test. Impact hammer test, I told you that here we, in the first test what we performed, free vibration test, we have applied the displacement and your structure is vibrating on its own elastic property. Now we apply the impact, right? This is the impact hammer, and here when we apply the impact, this is the hammer. When apply the impact, here the sensor is placed. Now this sensor will sense how much energy is applied, right? How much energy is applied, and this is the sensing wire which is attached to this impact hammer. So it will record how much energy is applied and how your system is vibrating, right? So here you can see what you have to do. You have to apply the impact of this hammer to this model, right? So when you apply the model, then we know how much energy is imparted and how your structure is vibrating, right? So look at this, the second part. You see, this is the spring mass system, right? Look at this. This is the spring mass system, and in which you are disturbing it. Now what is happening? This spring mass system is vibrating on its own elastic property, right? On its own elastic property, and the response is captured through the sensors. The sensors are placed at the top, right? So again, I'm repeating this. You can see the impact is given on the model, this spring mass model, and is vibrating on its own elastic property, is a free vibration, and the record is captured. All right. So we know again the frequency and the damping in the system. Frequency and damping in the system, right? So these are the known as a free vibration test. So you can perform this free vibration test on any models, right? And you see, it is very simple to perform, and it will give you the natural frequency of your structure on your model, right? It will give you the damping present in the system. These two important parameters you will get through these two tests, right? Then we go to the shake table test. The shake table test, the vibration properties of the structures are determined by varying the frequency of the shake table through the appropriate range, right? The shake table, we can apply the random motion, right? We can apply the same type of motion or harmonic motion for a longer time even. It depends, right? So we'll measure the frequency response curves, right, in form of a acceleration versus time, or we may have a accelerations versus forcing frequency, and that can be plotted, right? So we perform the shake table test where we get the natural frequency of the vibration, right? And that that can be done, right? So now we'll take a single story building, right? This is the single story building. Single story building having a larger mass at the top, right? Here the slab is located here. So heavy mass is at the one level, right? So if you want to model, you understand, we are not able to analyze this building directly, right? So you have to convert your building into mathematical model, and then once it is converted into the mathematical model, and using the principle of mathematics, you are analyzing, right? This is what we are doing. So we are converting this single story building into a model. So what we are doing, so this is the structure where the heavy mass is located here, right? And then this is the mathematical model we are saying, and then we are converting this structure, we are converting into this mathematical model. This is a mathematical model. We are knowing that this is the heavy mass is located at the top. This is the heavy mass. It is connected with the connected with the column. So this is a spring. The spring will represent the column, and this is the damping present in the system, and this is the external force which is acting on it. So we are showing the external force acting on the. So this is the free body diagram, right? This is the free body diagram, and if you solve it mathematically, you can solve and you get the response. So this is a single degree of freedom system, and what is the frequency? The frequency of the system is omega is k by m, or Fn is 1/2 pi square root of k by m. Here the stiffness is maybe considered 12 by L cube, 3 by L cube. It depends on type of support condition, right? So now 1 minute. Shall we continue from this, or shall we continue tomorrow, participants? It is already 4:10, so shall we continue? Hello, I'm not receiving any response. Anyone? Shall we continue? Or
dear participants, whether we continue or not. Sir, it's almost 4 and 5, so we can terminate the sessions here.
okay. Okay, I don't mind.
Okay, as you say, sir.
Yeah. So if you want to, because still we have numbers of experiments to show you, so it requires a lot of time. So if you want to continue, I can continue. Otherwise, we'll continue tomorrow. These experiments are very interesting, I tell you, and you will understand the dynamics as well as the structural behavior, both the things at a time, right?
Yes, sir. Please continue.
Continue. Okay. That is fine. So I'll continue with this. So we have a project of development of earthquake lab with Gujarat State Disaster Management Authority. So we have developed a shake table. Now we require the another part, that is the model. We have to develop different models to understand the structural behavior, right? So we have developed a spring mass model. Now this spring mass model, basically it is a single degree of freedom system, right? So we are knowing that in this case a heavy mass is located at the top, right? Heavy mass, and it is supported on a wall. This is the wall, so it is supported on a wall, and maybe if it is basically a masonry structure. So walls are the primary structural member, and then we have model like this, that there is a heavy mass at the top. There is a heavy mass at the top. It's supported on the columns, right? So we developed a spring mass model, and with the different properties, right? Which are the different properties? For example, we are knowing that our structure is made up with the different materials. It is made up of steel. It is made up of RCC. It is made up of the wood. It may be a composite. It depends. If you change the material, then the behavior will change. So the one parameter we kept as a variable is a material, right? Then we are knowing that the height is very important. Height is very important, right? If you change the height, for example, if I'm changing the height, if I'm considering the height is L, for example, then I'm knowing the stiffness is 12 EI by L cube. But if I the height, if I'm reducing the height, or if I'm going for the double height, for example, sometimes in the bungalow we are seeing that uh, uh, instead of single height we go for the double height in the bungalow, right? So if we make it double, then what is going to happen, right? Then it is 12 EI upon 2L cube, right? This is the difference, right? 12 EI upon L cube and 12 EI upon 2L cube. So its stiffness will reduce 8 times, right? So this is happening. So we have to study what is the effect. If your structure, if you increase the height, your structure will become flexible. If you decrease the height, your structure will become stiff. And we are knowing that the earthquake load is distributed as per the stiffness of the vertical element. So height is very important for us. The third parameter is the mass. We are knowing that sometimes we are placing the normal slab, sometimes we are placing the flat slab. Now flat slab is having a higher mass as compared to the normal slab, because we are knowing that we are eliminating the beams from the flat slab, and therefore what is happening, the mass will become very high. And we are knowing what is earthquake force. Earthquake force is mass into acceleration. F is equal to ma. So if mass is increased, earthquake force will increase, right? And the last parameter we have changed is the thickness, or you see, if we talk about the columns, the columns is having the size 300 by 500. It may be 300. If you change the column size from 300 to 500 to 300, 800, 300 by 800, then stiffness will change, right? So we have to understand this thing, and we try to we try to develop the model. So a simple models have been developed, right? So this is the spring mass model having a single degree of freedom, and you can see here these are the models we have developed in 2006-7, and still it is working. I tell you, these all are still present in the they are in the working condition, right, after 16 years. So they are made up of good material. And you can see here the heavy mass located at the top means it will represent the slab, and this portion, this will represent the column. So it is like this spring mass model will represent the single story building, having the different material property. The one is made up of stainless steel, another is made up of the flexi ply, this is made up of brass, then this is the copper, right? And we have perform a test on it, and this is the shake table test we perform, and then we get a record, right? Now what record we get? This is the acceleration versus time, acceleration versus frequency. Now as it is a single, I tell you, it's a single degree of freedom system, so you get a one peak, right? Now this will tell you what is the frequency of this system, right? This is the curve of acceleration versus frequency. So at the resonance you get this response, peak response, right? And you get the frequency, corresponding frequency, right? This is what we perform. Same way in the stainless steel model we have performed, in the flexi ply we have performed a model, right? You can understand, you get a single spike because it is a single degree of freedom system, right? So here I want to show you how we perform the test, right? So just look at the test. This test is very important for us. You see, here we are placing 4 models, right? There are 4 models. Now these 4 models are placed on a same plate, right? So same motion is given to all the 4 spring mass model, right? Now they are made up with a different material. The mass is same at the top, all other parameters are same, right? Only changes that the material, right? Material means we are changing E, right? We are changing E. Okay, I'll explain that part because that is to be needed. Sorry. You see here, if we if we change the material, we are playing with E, right? If we change the height, we are playing with the height of the structure or height of the column. Here we are playing with another parameter, that is the mass. And here we are talking about the dimension of the column. It is B cross D, right? So we are changing this direction. So we are playing with this four things, right? So here you can see this. These are the four models placed on shake table. The same motion is applied. Now we are knowing that the frequency of all the four are different, right? And already we have calculated the frequency of all the four models theoretically. So we are knowing which model is stiff, which model is flexible, right? So initially we are knowing, and then we have fabricated this. Now we apply the same motion. What is happening? Just look at it, right? So this is very important for us to understand the concept of resonance. Concept of resonance. So first of all, low frequency is applied, very low frequency. Now you can see out of four, only one model is vibrating, right? Whose displacement is higher, right? Now what is happening? Now I am increasing the frequency. I am increasing the frequency. So now the first model is vibrating less, and what is happening? The other models start vibrating. Look at other models. Now the second model is giving higher response, right? It means this frequency is matching with the frequency of this particular model, right? So that is known as the resonance. So frequency of shaking is matching with the frequency of model. So this is the second model. Now again I'm increasing the frequency, right? Now look at what is happening. If I increase the frequency, the first two models slow down, and now the third model start vibrating. Look at the third model, right? So it gives higher response. So now it's entering into the resonance, right? Look at the response. Yeah, that is the response, right? So, and now still I'm increasing the frequency. Now look at what is happening. The first two, three are not vibrating, but now the fourth start vibrating, right? Because the fourth, this one is the stiffest. This is the stiffest model we have. So it is having the highest frequency, right? This is having the highest frequency. So on a higher frequency, it is vibrating. Other three are not responding because those frequencies are not close to their frequency, right? That's why they are not giving a response. Right. So this is the classical practical, in my opinion, to understand the concept of resonance. Concept of resonance, right? So again, I want to repeat this, right? Just go through this again. Just go through it again, and just try to understand the concept of resonance. Concept of resonance. First, the frequency of shaking is very low. So now you understand that the first model is having the least frequency, and this model is having the highest frequency. So at the low frequency, what is happening? The first model is responding. Now frequency is increased. Now if frequency is increased, then the other model start responding. But which model is giving the highest response? That we also see. Now you can see the second model start giving the response. It is made up of flexiply, right? Now it is giving the highest response. Now again we are increasing the frequency. Now the third model start responding, right? Now look at the third model. Now response is not built up because we have to increase the frequency. We are increasing the frequency. Now the first two get slowed down, and the third system is vibrating more, right? And now you can see this is the stage of resonance. Yes, this is the stage of resonance, right? For the third model, but other three are not responding. And if we increase the frequency again, then the fourth is responding to it, right? So this is the fourth one, right? So this is how we can understand the concepts of dynamics, right? Now if the student will see such things, then he will never forget this thing in his career, in his life, right? He will understand what is resonance. So resonance is perfectly explained through these models, right? So what we do, again, we will plot the curve of frequency versus acceleration, and we get the peak, which is the frequency of. Now what we do here, again I'm saying, only perform the experiment is not okay. So what we do, there are four: mild steel, stainless steel, flexiply, and brass. So what we have done, we have some result of theoretical values of the frequency. Look at the frequency, right? 3.4 hertz, 1.52. These are the frequencies we find out theoretically, right? Then the same thing is modeled in the stat, right? And we get this frequency. So this is the theoretical, this is the frequency we received in the stat software, and this is the experimental result. This is the experimental result, remember. Now these are in very close range, I tell you. So the only thing is that the condition what we are assuming in the software or theoretically is quite, it may be slightly different from the experimental condition, right? So here you can see the theoretically I'm getting 3.4 hertz frequency, and when perform the test it was 3.05. It is 1.52, it is 1.15, 3.27, it is 3.25, this is 3.02, it is 2.8, right? So you can validate the result and you get the confidence, right, to perform the test. So before you perform the test, you have to ensure that you know everything about your model, right? Once you know about your model and then you perform the test, then you are going to predict the behavior of a model in a much better way, right? So then we have another model which is a variable height, right? So here I told you earlier that we can go for a double height column or a single height column. It depends. If you vary the height of the column, the response of your structure will change, right? I tell you, if suppose this height is L, right, and this is L by 2, for example, this is L by 2, right? The stiffness of this model will be the 8 times, because it is 12 upon L cube. So L by 2 cube means it is 8 times stiff. So it will try to take 8 times more load during the earthquake. So this part you would understand, right? So these are the results again, right? Again, we go perform the experiment and we get the result. These are very close, in a close range. So almost they are identical. So it boosts up our confidence. Then we have here the fourth model. The fourth model is having the variation in the mass. So here you see here this is having the lowest mass and this is having the highest mass, right? So we are knowing uh, the frequency depends on what? The frequency depends on stiffness and mass, right? So here only one parameter we are changing. It is mass. So here it will be basically, sorry, this is K by M, right? This is K by M. So here we are changing mass. So if mass is increased, the frequency will increase or decrease? It will decrease, because mass is in denominator, so the frequency will reduce, right? So again you can see, if you reduce the mass, the frequency is, you increase the mass, the frequency is decreasing, right? And I think the results are quite consistent. And the last model is the variable thickness, right? So we are placing the sensor at the top and we are recording, and this is the result of the fourth one. So the main thing is that you can validate your theoretical solutions with the practical, right? And always that is to be required when you perform the experiment, right? So I think this is the second experiment we have. It is a multi-story building, and um, I will show you the results tomorrow, because I think it is already 4:30, so I don't want to extend more. So we stop here, and we'll continue from this slide tomorrow. And we also talk about the other models also, where we are talking about uh, the testing of the masonry structures at the laboratory, right? So we discuss everything. We take the certain basic structures, and then we switch over to that part also, right? So thank you very much. Any questions you can ask, please. Participants, if you have any questions, you can ask, please.
Hello, sir.
Yes.
Yes, sir.
Yes, please.
Now I have one. Okay. So actually, sir, in a reality, actually, the structure is totally means non-homogeneous structures are there. Let us take the walls is there, RCC column, slab, and everything is there. And actually, the model is totally, it is a homogeneous material. Let us take whatever the plate is placed, that is totally homogeneous. So how we can synchronize all these results and all these things?
You see, the main thing is, like, that is what we are saying. When you are making the model, what is your purpose? You have to clear, right? Here, our main purpose is to understand the behavior part. So we want to understand the resonance, and we want to understand whether the theoretical concepts are matching with the our experimental result or not. So here we are testing it that way. Now, if we come to the structures, real structures. Now, in real structures, we have actual size, right? So in the laboratory, we are not able to test it. So there is a process of scaling down of the model, right? So if you scale down the model, we are knowing that the material is not consistent, is not homogeneous, but that is we assuming that during the theoretical calculation that it is homogeneous and isotropic, everything we are assuming. But in the real sense, if it is not, then your practical result will differ to some extent, right? But our assumptions are not so bad that your practical result and the theoretical results differ by a great amount. No, it is not happening. There is a gap. That is the one part. So if you if your assumptions are wrong, definitely it affects the results as far as experiments are concerned. This is the first part. The second part is the point of concern is when we are performing a test in the laboratory, then to create a condition, boundary conditions, it's always a challenge, right? So again, your experimental result will show that what you have assumed, what boundary condition you have created through the model, and what you are analyzing in the software, then you have a bigger difference in the result, right? So here again, I'm saying that our purpose is that we want to understand the structural behavior, right? And we, as far as the scaling of the model is concerned, you see, if you take a RCC building, then we always have certain assumptions. In case of RCC, that is a homogeneous, and uh, uh, we are assume the value of E in everything we are taking. Now, when we are scaling it down, then even the size also matters. If the size of your brick is in a real sense, and if you are reducing the size of the brick, then you have to scale down your model in such a way that your rear brick and this the brick you're using in the model will exhibit the same result. So always scaling is a challenge, and we have to do scaling before performing the test if you want to correlate the actual structure with the your model, right? So scaling is highly required. But as far as these models are concerned, again I'm saying we are talking about the instructional earthquake engineering lab, the instructional lab which exhibits the structural behavior, and we'll show you the what type of tests we are performing in our lab, right?
Okay, okay. Thank you, sir. Thank you.
Yes. Any more question, please? You can ask.
Sir, do we need to calibrate or validate this type of the model?
Models to be calibrated, I don't understand you. We have a model, and when we have this model, theoretically we are knowing the values, and when we perform the test on a shake table, and then when we are matching these two, right, then we understand that okay, uh, if they are coming close, it means what we assume and what we have performed, they are quite correct, right? Now validation in a way, like material property, right? So if you suppose if I'm going for any model, and I'm using the different material in my model, then I have to test all the materials before my test, and I must know each and every property, and then I come to the correct solution, right? Yeah. Is my answers is okay for you, or is clear your doubt?
Okay, but just I would like to know that its validation process is required in this case or not. Only that
Yes,
I want to know.
always we are, you see, suppose we are, when we are performing this test manually, we are, for example, manually we are counting the frequency of this, right? And then we are testing through the sensors. We have to calibrate our sensors and everything, I tell you, that is required. So for example, how much frequency your shake table is generating, we are placing a sensor on it, and we are uh, taking the record of it. So we are knowing that this is the frequency we are getting at this particular time, right? At the same time, the sensors must be calibrated, right? That is to be calibrated uh, uh, by the professional agency, that is required. But model validation, uh, that you are creating, so while creating the model, you have to ensure that what type of support condition, what type of boundary condition you want, and accordingly you have to ensure that boundary condition during the fabrication of the model, right? So validation of that can only be we get when we compare the theoretical result with the experimental result, right? But validation is always required wherever possible.
Thank you, sir.
Yeah. Okay. Any more question, please?
Yes, sir. I guess there are no more questions from the participants as of now. So we can bring this session to an end.
Okay.
Okay. So
Thank you. Thank you very much.